In Chapter 2, we talk about circles and the related properties. First, we look at Section 2.1, Basic Properties of Arcs and Central and Inscribed Angles. Definitions. A circle. In the plane, we have a fixed point, and the circle is the set of all points in the plane at a given distance from this fixed point. So the fixed point, we call it a center, and the given distance we call it a radius. So for example, if you want to find out all the points such that the distance from this fixed point is 3, then we can generate a circle. Congruent circles. If we have two circles, when we call congruent triangles, we have a similar definition, congruent circles. So if we have two circles and they're congruent if and only if their radii are equal. So it's a lot easier than congruent triangles. So we just need to compare their radii. Next, second, if we have a circle and we can draw a line that intersects the circle in 2 points. For example, L here in the picture. L intersects the circle at point A and point B. So this is called a secant. A chord is the line segment connecting the 2 points. So for example, if we only consider the segment between point A and B, this can be called a chord. And similarly, PQ is exactly a chord. And diameter is a chord containing the center. So in this picture, AB and PQ, they are both chords, but they are not diameter because they are not passing through the center. So if we look at last picture here, this chord that passes through the center, so this is a diameter. So diameter is a very special chord. And the line M here is a tangent line because it intersects the circle only at 1 point. So if a line intersects the circle at 2 points, it's called a secant. But if it intersects the circle at only 1 point, that's called a tangent. And we're going to talk about the tangent line to the circle later. Suppose we have a second line intersecting the circle at AB, which is not drawn here. So the line segment between point A and B, it's called the chord. So this chord AB will cut the circle into 2 arcs. So that's a big arc and that's a small arc. So we call the larger of the 2 arcs a major arc. So the dotted arc is the major arc, and the smaller one is called minor arc. So the red arc here in the picture. And a central angle is an angle whose vertex is the center of the circle. So if we draw 2 line segments, so we're connecting this is the vertex, which is also the center of the circle, and we connect the center and the 2 points on the circle. We get an angle. So this angle here is called the central angle. So the degree, for example, we can measure this angle. It's either we can find out the degree, the measure of this angle. And next, we're going to talk about the definition of the measure of arcs. So we know if we have a line segment, we can measure the line segment. Say maybe it's 1 meter, or maybe it's 1 feet, or 1 foot, or 1 inch. How do we measure the arc? Well, the definition here is the measure of. We define the measure of a minor arc. So this red arc here, we use the degree of the measure of the central arc angle to define the measure of the minor angle, minor arc. For example, if we measure, so this is the central angle corresponding to this arc here. If suppose we measure it, it's 60 degrees, and then we can say, okay, the measure of the minor arc is 60 degrees. And what about the major arc? So the started arc, we use 300 degrees minus the measure of the central angle. So suppose this alpha is 60 degrees, so we know by the definition the measure of this minor arc is also 60 degrees, and we know the whole circle is 360 degrees, so the rest of it will be 360 minus 60, so that would be 300 degrees. So the measure of the minor arc, major arc, is 300 degrees if alpha is 60 degrees. So this is it's different from the how we measure the line segment. If we talk about the length of an arc, that would be different. The length of arc, for example, we can use a rope. Suppose we have a rope around the circle, and if we want to find out the length of this arc, we can cut the rope and this piece of arc and straighten it, and we can use a ruler to measure it, measure the length. But here, when we talk about measure of minor arc, we simply use the angle. So when we say the measure of the arc, it's the same thing as saying the measure of the central angle. Similarly, the measure of major arc. So this is a little bit different. This definition makes sense because the bigger the central angle is, the longer the corresponding arc is. So we can when the central angle gets bigger, for example, from 60 to 61, 62, 63, when it gets bigger, the arc also gets bigger. So it kind of makes sense to define the measure of the arc as the measure of the central angle. Next one, we talk about adjacent arcs. So if you look at the picture here, we have arc from x to y, that's an arc, and then from x to b, that's another arc, and then we have BA and AY. So we have 4 arcs here on the line. Adjacent arcs, for example, x and y and bx, they share only one common point, x. So these two, bx and xy, these two arcs are called adjacent arcs. They have arcs that have exactly 1 point in common. Congruent arcs, it's like when we talk about congruent, arcs in the same circle or incongruent circles that have the same measure. For example, if we look at xy and BA, these two arcs, they are both in the same circle, and the measure of, if we check the measure of each one, xy, by the definition from last slide, that we check the central angle, which is 70.36 degrees, and then we look at the measure of the central angle corresponding to arc AB. It's also 70.36 degrees. So these two central angles have the same measure. So the corresponding arcs, these two, xy and AB, we say they are congruent arcs. So from a picture, it's very easy to understand the definition. So for now, if we want to compare the arcs, we only need to compare the central angles. Now next we have talked about 4 propositions. The most of them are very easy, so we will skip the proofs. The first one, let's look at the first one. Two minor arcs in the same circle or incongruent circles are congruent if and only if their central angles are congruent. So this is what we just talked about before. So if you look at this picture here, AB and CD, these two marked angles are central angles corresponding to each of them. So suppose these two angles are congruent, then the corresponding angles, minor arcs are congruent. So that's very easy to understand by the definition of the congruent arcs. The second one, proposition 2.2. In a circle or incongruent circles, two arcs are congruent if and only if the corresponding chords are congruent. So if we look at this picture here, we have two chords and they're both in the same circle. And the corresponding, we have two arcs, arc AB and arc CD. So in order to, from proposition 2.1, we know if we want to know if AB and CD are congruent, these two arcs are congruent, we can join the center and A and B, center and C and D. Then we get two angles, and we can compare the angles, see if they're congruent. But proposition 2.2, instead of checking angles, we can also check the corresponding chords. If these two chords are congruent, the corresponding arcs are also congruent. The proof is very simple. After we join the center and ABCD, we get two triangles, and these two triangles are congruent. We can use either side if we know these two chords are congruent to prove these two triangles are congruent, or we can use side if we know the two central angles are congruent to prove the chords are prove the two triangles are congruent. So because this is a if and only if condition, we need to prove not only necessary but also sufficient conditions. So for example, if we know two arcs are congruent, arc AB and arc CD are congruent, then by proposition 2.1, their corresponding central arcs, the central angles, if I use O to denote the center in the picture, so the central angle AOB will be congruent to the central angle COD. So, and because it's in the same circle, or even in congruent circles, they have the same radii. So the AO will be congruent to DO, and BO will be congruent to CO. So it can be very easily proved that these two triangles are congruent by angles, side. But if we know so that's the proof. If we know two arcs are congruent, then so if we can prove these two triangles are congruent. Of course, AB and CD, they are corresponding sides, so they are also congruent. So we proved if two arcs are arc AB and arc CD are congruent, then the chord AB and the chord CD are congruent. Vice versa, if we know the chord AB and the chord CD are congruent, we can use side to prove these two triangles are congruent. And then, of course, if the two triangles are congruent, the angles, corresponding angles are congruent. So these two central angles are congruent by proposition 2.1. If the central angles are congruent, the corresponding arcs are congruent. So AB and CD will be congruent. So we can use congruent triangles to prove proposition 2.2 easily. So I will skip the proof here.